nice. It's at least audio, if nothing else. All right. So let's actually do a little review. So what's the derivative of this here? Or what is, evaluate this? So do that. Shut. No. Appreciate it, but do it. Everybody. Just wait for someone to say it. Try it out. I tell you honestly, this level, this should be a thank God problem. Okay, please, Jeff, give me more of this. Derivatives are almost never hard. You just have to remember the rules, and they fall into place. Try something out.
In my head.
Hmm?
In my head.
In your head?
Yeah.
Neat. Good real meaning of the long base through. Yeah, that should be. So the way I try to look at this is, and the way I teach this, is you have to be able to find the inside function and the outside function. At this point, that should be second nature for us. We know what the inside and the outside. Since the derivative in the natural log is something. I don't care really what that something is. What's the rule for natural log? 1 over that thing. Then what rule kicks in?
Chain rule.
Chain rule first, right? Chain rule says you have to do the derivative of this piece here. And of course, when I first teach this stuff, I try to tell people to write the rule first, and then do the derivative. So what we get in trouble is we try to do it all at once, and we forget a chain somewhere or something weird. So this little piece is going to just come with for the ride. What happens in here now?
Product rule.
Product rule. Derivative x squared. Leave this guy alone. Plus.
X squared cosine.
So x squared cosine 3x
Times 3.
times 3 for the chain rule for that piece, right? How are we doing so far? And actually, that's it, right?
Yep. That's it.
So that mess over this mess, and you could reduce it. 1x cancels out of everybody there. It looks like break it up, whatever the hell you want to do. After that, it's just clean up, right? But that's the derivative. Okay. So that's chain rule is it's you take the derivative as if this is the natural log of x of something. It's got to be 1 over that thing, and then the inside's got to get its term. So I like to think of it a lot like product rule. We do derivative of 1, leave the other guy. Well, he's got to get his term. Plus, okay, give the other guy his term. So how the hell does this work with vectors? Well, exactly the same freaking way. So if I have v of t equals why not? I enjoy it. What is v prime, let's say, I don't want to write this, d by dt of v of t cubed.
We just
I like
take the derivative, plug it in.
two ways to do this. One way is really kind of neat. There's never a way that I've directly taught, but I just now, when I was looking over this before class, I thought that's an interesting way to put this. What you do is you take the derivative of v, but you plug a t cubed into it, right? And I don't know if some teachers probably teach it directly that way. I kind of teach it a different way. I teach it, like I just said, natural log of something is whatever that thing. What is the derivative of this going to be? What is v prime of t?
2t.
Okay, 2t. Who remembers this thing?
Natural log of 3 times 3 to the 2.
Yeah, so it's 3 to the t, natural log of 3. Remember that? The only reason that e to the t is its own derivative is because natural log of e is 1. There's that natural log of the base piece on there. And same kind of thing happens here, really. Just like natural log, the first step is the same, except it's not a base e, it's a base 3, so, and it's on the bottom. So that's one of the easier ones to forget the derivative rule for, is the any base exponential or the any base log. It's a little freaky. So the derivative of this is equal to v prime evaluated at t cubed times the derivative of t cubed. And this step is what? Chain rule piece, right? This is kind of a little bit different way to attack it than what I did over there. They give you a general function. They ask you what's the derivative if I plug a t cubed into it. You can just do this guy's derivative. Now plug a t cubed into what we got. So what do you get here? This will be 2t cubed. And 1 over t cubed natural log of 3 times the derivative of t cubed, which is 3t squared. And then you can multiply that in and simplify it, right? Put the major there. Just make sure you understand. I'm sort of unhappy now that I did that first, because I don't want you to think it's different from that. I mean, what is v of t cubed? What is v of t cubed? And these should be vectors here, but I think you're cool. V of t cubed would be
t to the 6 plus 2. 3 t to the t cubed.
Yeah.
Log base 3 of t cubed.
Okay. Now take a minute and figure out the derivative of that. Are they going to be the same? Okay. Because that's what we're doing there, isn't it? And they do it that way in the book, page 733. V prime a t squared. They actually just plug a t squared in there.
So you could do it directly or chain rule?
The chain rule is still there. I mean, this piece is the chain rule piece. Yeah. I want you to realize we do derivatives this way already. Like the sine of t cubed. What's the derivative of that going to be? What's the first thing you think of when you say, okay, what's the derivative of that? What's the first thing you think of? First thing you worry about?
Cosine.
It's a sine. That's the first thing I worry about. Now, part of you guys worry about this first thing. You shouldn't. You say, okay, it's a sine. The derivative of that is a cosine. So the first step is really just take the derivative of as if it was sine of t and then plug that back into it. That's really what I'm doing over there. And then, of course, this guy's got to get his term. Right? Okay. So I kind of like that. It's a nifty, it's the same math, but it's an interesting way to look at what you're doing with the chain rule. If you don't understand what I just did, just do it the way you always did it. Right? There's nothing new there, really. Which is reassuring. So, I mean, they will have, like, when they say product rule, we have to be careful about what they really mean. Here is what a product rule would look like. Because what's the product? There's no real good, there's not a product for a vector. So what we mean when we say the product rule, it refers to non-vector function times a vector. So what I mean by that is something like this. Take the derivative of, I don't know, e to the 3t times t squared t negative 1. So that's, you could look at that as a product rule, right? So what's, and all these rules are on page 732, by the way. So what's kind of funny about this? Do you guys see anything? Yeah.
Is it a less than sign?
No, these are vector signs.
Oh, okay.
Yeah. So in a way, you're right. It is a less than sign. Just don't read it like that, because I'm not sure how you would do that. Just take the derivative as inequality. Does anybody, and again, now this sort of relates to this. I kind of like to do this example when I'm teaching product rule and stuff. X cubed, I can look at it as if it was x times x squared. If I take the derivative of this, I just do this straight up, exponential rule. If I take the derivative of this, the way I've got it written, I'd have to do product rule, but of course they better come out the same way. So just me saying that, what's the interesting thing to do first here, not really have that product rule to worry about? Yeah, just multiply this stupid thing in. And then you don't really have a product rule to worry about, right? And we know that's allowed. We can multiply at any specific t, this is just a constant, that can go inside, no problem. So the product rule there to me is kind of funny. I never really did it. I just took that stupid thing inside. Unless for some reason there was, some reason I didn't want to do that. Now here, would it be easier to do it without bringing that in? Yeah. So what would this be here?
3e to 3t.
Good, 3e to the 3t, and you keep this the same, right? So thankfully the product rule is just the same as what we're used to. Derivative of this guy, leave that guy alone. Plus, leave this guy alone. Derivative of this guy, which would be
1, 2t, and 1 over radical.
I like it, right? Now you got some more cleanup here to do, but that's not a bad trade-off from what would have been 3 individual product rules, right? If I would have brought that in. Okay. Either way to do it is fine. All right, yeah.
So, do we stop here, or do we have?
Oh yeah, now it's cleanup, right? Now you can bring this in, add your components together, right?
Then do that.
Would it be easier to take the e to the 3t out of the equation and then add them together and then put it back in?
How do you mean take it out of the equation?
Like,
I can't take that out here.
No, I mean like, after you put it through and did the.
Oh sure, yeah. Now you can take the e to the 3t out, yeah. Sure, that's fine. Or not, I don't care. But after this point, it's just cleanup, right? So if you want to take the e to the 3t out, then you have 3t squared, 3t negative 1, plus 1, 2t, negative t, negative 2, and I just put your like terms together, your components together, right? Okay, so the cleanup is not that bad. Okay, cool. And this is, again, I want to be careful. I want to really stress that a lot of what we're doing is exactly like we were doing before, but the trap you got to watch out for is to think it's going to be that way for every damn thing you do, which obviously it can't be. It's already been different on a few things. Like just freaking multiply. We have 2 different ways to multiply. The last little piece in here is what you should expect the next step would be is talking about intervals. So I could have a definite integral of a vector value function. That's just a neat phrase to say. So I could have from like 0 to 3. Oh, I don't know. Tangent t. Square root of t. Doesn't matter. And t. Yeah. And you tack this the same way, right? Just integrate again. Does anybody know off the top of their head what the integral of tangent is?
Natural log of cosine. Natural log of negative natural log of cosine.
Because it depends on if you take the natural log of the secant or the negative natural log of the cosine.
I do know this.
Right? You guys remember that? The integral of the tangent?
So 1 over 1 plus t squared?
Say again?
1 over 1 plus t squared?
Now you're thinking about, well,
Oh, that's inverse tangent.
yeah. So if I thought it was natural log of cosine t,
You just
what's the derivative of this? And of course I'm doing something on purpose.
cosine, negative sign over
1 over-
cosine.
Yeah, so negative sine over cosine, and I want it to be positive tangent, so I need to do that. So one way is negative natural log of cosine. Now why can I write that as natural log of secant, of course, why? Why is it the same thing as natural log of secant? Because the negative exponent, and then the negative coefficient becomes the negative exponent. Cosine inverse is secant. Or not cosine inverted, you know, cosine inverted is secant. Cool. You guys doing okay? So I'm not going to make you, if you didn't remember that, normally if I'm going to give you a problem where eventually I have some funky integral that I never made my students before memorize, and I'll try to be kind of specific about what I make you guys memorize. You can either come up and ask me, or I'm going to have like a little table like I did on the pre-test. Right? You can look it up and you hit one that you need. Okay. The rest of that should be easy. I mean, do we have to go through this? It's really just integrating each piece. So we got the first piece done to a point, right? Let's say natural log of secant. What's the integral of t to the 1/2?
2/3 t to
T to the 3/2. Okay, I like it. And the integral of t?
1/2.
11. And that's evaluated from 0 to 3. And then you just plug stuff in, you go to 10. Okay. Seriously. What did you say, please? Cereal. If you don't get my references, you'll think probably think I'm crazy no matter which one you go. All right. There's really nothing surprising in 11.6 about how to take the derivative, how to take the integral. There's nothing really surprising. One little thing I want to make sure that I'm clear on, we did that tangent vector before. And how do you find the tangent vector? Just a tangent vector for a given vector valued function.
Find the derivative.
Yeah. So the tangent vector would be r prime of t. Now, I got myself into a little trap last time about I wanted to make a point that the circle is really the only one where the velocity would be 90-degree angle to the actual position vector, right? And we see that like I was saying last time, you see that like there. But I could certainly have a vector, a straight line, where at any point on that line, the position vector is in the same direction as the line. So the slope and the position vector will be parallel. Maybe. Okay, cool. And one last point I want to make before we get into some homework stuff. Remember I had this analogy, this was a good old line, and what's the derivative here? M, yes, good. Derivative is slope. And then if I have this guy here, what's his derivative going to be? Yeah, exactly. A, B, C. Because these are all constants. That'd be like the 0 vector. T goes to 1 times this. So it's exactly the same. In both cases, they are the M piece, right? The slope piece. Derivative will always tell me slope, even if I got it written as a funky vector value function. Right? Okay, so what I want to do for a little while here is to let you guys work on whatever homework section you want to work on for a little bit. Then we'll take a look at section 11.8. We're not going to finish it today, just a little preview of it. Then we'll head out. Take out sections where you have questions that you've run into that you didn't know what the hell to do, or get into a brand new section if you want to.
Oh yeah. Do you want me to stop recording? Yeah. You want me to stop recording? Oh yeah, thanks.